All right, so great. So welcome to the session 2 of deep learning. In this session, instead of going ahead with the TensorFlow deep dive, so we based on some of the feedbacks, we realized that it will be better to do an end-to-end project quickly, and then we go ahead with the usual TensorFlow. All right, so today we are going to go really fast in the end-to-end project that would actually help you get up and running with machine learning. So some of the parts we are going to skip in this session in the end-to-end project, which is not required. So it's not going to take that much time. All right. So what I would suggest everyone that they should basically do the hands-on along with me. Okay. So since most of the other people who are part of the course have finished the machine learning section where we covered the end-to-end project, that's why they have not joined today. Okay, that's why they have not joined today. And some of other members who have joined only deep learning, they have already covered machine learning earlier. So for them probably it may not have been for much use. That's why we have right now 3 attendees. That will be very good for hands-on, so that I'll be able to quickly debug and look at the screen and help you out, and will be also able to finish it during one session. All right, so it's an end-to-end exhaustive project. This would help us get up and running really quickly and would give us the entire picture of our machine learning project. Good, so let's get started. All right, so let me, okay, by mistake I unmuted Shiva. So all right, so first of all, let's just start with the project, and what we'll do is we will check out the code and then we will start executing it step by step. Okay. All right. So this is an end-to-end machine learning project. This will give you an overview of how does a machine learning project looks like. So in this project, we are going to walk you through a complete cycle, and it is completely okay that if you don't understand few of the code snippets, you can always go back or you can always dig deep to understand a particular concept. So the first step is to set up this repository, as in the notebook. So you will need to clone this repository. If you have already cloned, then you don't need to worry about it. So you could just go to Git. You just go to new terminal and do the Git clone. Okay, and I'm going to send it to you, all of you, over the chat. So all right, so this is the command that we need to execute in the terminal. All right, so in the terminal, again, when I go to Jupyter, we could open a new terminal, and so I'm at my labs. I clicked Jupyter and it opened Jupyter Hub here. I'm starting my server. All right, now here we could just click on new terminal. Okay, and copy paste that command. It says git clone, and for me the ML path already exists. So this ML path is already existing. Therefore I'll go to ML and say git pull. All right. So git pull basically brings the latest notebook from the server, latest code or latest snapshot of the repository from the server. Okay, so are you able to do it, everyone, quickly? Okay. Hi, Ross. So, Ross, it is the same thing that we did earlier on the end-to-end project, just a little tad faster. So, it's going to be really quick. Okay, so James has done, and Shiva. Okay. So all you have to do is go to home, as in the My Lab, click on Jupyter, then start the Jupyter and start the terminal, and inside the terminal you say git clone and then do git pull. All right, should I move ahead? Yes. All right, moving ahead. If you have so make sure that whatever we are doing here, you should do it along with me. Only then this will be useful to you. Okay. If you are stuck, just let me know. I can take a look at your screen and will be able to help you out. Binta, James, Siva, and Ross, should we move ahead? Great, wonderful, wonderful. So all are set. So this is one part of the session that takes most time, just to get up and running in the beginning. So great, great. Now, once we are done with that, go back to the full screen. All right. So these are the steps that we are going to follow one step at a time. So first of all, let's take a big picture. Take a look at the big picture. We're going to build a model of housing prices in California using the California census data. So basically, we have the prices of houses in California, and we would like to predict we would like to build a model that has the capability to predict the price of a house given the details. So this is what the objective of the end-to-end project is. So first of all, we are going to look at the data. Okay, we are going to look at the data. Now, how to look at the data? Open the notebook here, go back to the folder here. Okay, in this, locate a folder called ML, then machine learning, and then I have basically created another version of end-to-end project, which is specifically for going over the end-to-end project really fast. Okay, the one that ends with bootcamp. Okay, so this is what we have here. Are you able to open the Jupyter notebook? All right, so the first step is that we are importing a library called pandas. Pandas helps us manipulating data in the form of data frames, and it provides various utilities to process structured data. So that is pandas, and then there is OS. OS is for dealing with the file, dealing with processes. The package OS is code to the Python. All right, so Next is that we are defining basically a variable called house path, and then we are defining a method called load housing data. Okay, so all it does is it reads the CSV, and where it is going to read from inside the folder datasets and housing. Okay, so inside the folder datasets and housing. So there is a file called housing.csv. It's going to read that one. Okay, for me, it is not, it is opening somewhere else. All right, so this is the file that we are going to deal with. So we defined a method first, and then we basically loaded it. A question from Bintao is that why do we need to import pandas and OS? Actually, the OS one is only for creating this path. It's not actually again required. The same thing could be easily done using a statement like this. Okay, we could do. Okay, we could do. All right, so this is also very much possible. Okay, very good question. Let me just try this one. Okay, so this is also completely okay. This kind of approach, we are loading it here. You can see that. So this is very much okay. Okay, so you have the, so pandas is something that we are using to read CSV. Okay, so there's a very nice function called reading CSV, and for reading CSV in pandas, which basically handles the complex structure of CSV files. All right. So we basically deal with the, so pandas provides various utilities such as reading from CSV and reading from tab separated, and pandas also provides many functionalities to slice and dice the columns and rows in a data frame. So that's why we are going to use pandas. All right. The OS wasn't really required. OS was basically required to join these two. So we kind of can skip it happily. All right. So the same thing is happening here. Okay. Quick question from Shiva. Thank you, Benta, for the question. Is that what you needed? So could you give us a picture about their all parameters and give us an explanation about some important parameters and details? Sure, sure. So basically, the pandas itself would take a bit of more time to explain. And if you're looking for just say this function, right, you could take a look at here. Let me show you that. So you could just take a look at this part. Okay. So it gives you all the information about all the parameters on reading CSV, whether it has header or not, whether it has if you want some other delimiter than comma and so on. Okay. So you can see that. Oh, okay, so this would be a quick way to look at their documentation, and also you can take a look at PD dot, and it shows you all kinds of functions. Okay, it shows you all kinds of functions. Similarly, once you have created a data frame, you could also take a look at all the functions a data frame provides. Okay. All right. And most of it we will cover as we go ahead. Okay. All right, good question. Now, next question from Shiva is, could you quickly let us know the keyboard shortcuts to run the command? Okay, keyboard shortcut is Shift Enter to run the command. Okay, it is Shift and Enter together. Also, if you want to insert a cell here, you can press A. Okay, so A is for inserting a cell above. B is for inserting a cell below the current selection. Just remember that you have to select outside or press escape to go to non-editing mode. Okay, command mode, you can say. You can, like, here I am right now, I'm in editing mode. Okay, I can go to the command mode by pressing escape. Okay, so X is for deleting. Okay, this is below it and right. Good. So this is and then Shift plus Enter is for running. Okay, if you want to just write some formatted text, you can change the format to Markdown. Okay, and then you can use a format called Markdown, which is basically very simple format. Okay, so here I just created a heading and you can see that. All right, so that was a quick way of okay, so take a look at more command settings here. There is keyboard shortcuts, so you could take a look. Okay. Great. I hope that would be good enough for starting. All right. So because you're going to spend a good amount of time inside Jupyter Notebook, so make sure that you are comfortable with most of the, you become comfortable with Jupyter. Okay. And it'll become more efficient if you start using the shortcut keys. All right. So that's first step, that we have loaded the data. Wonderful. Now let's try to frame the big picture. As we as we saw, we have many columns in this data frame. You can see there are so many columns, and some of the columns are like population, median income, median housing prices, and so on. So this data set is not per, the data set is, it's not the data per house, it's a data per block. Per block is basically like a small neighborhood, and in this neighborhood, what all houses are there, it is this data about them. It is the data about per block. It's not a data about housing, right? So that's why we have longitude, latitude of this block, then housing median age, the median age of the housing in that block. That's why we are using median. That's why using median, not housing age. Had it been per house data, it would be house age. Then we have total number of rooms, total number of bedrooms in this block, and total population in this block, and how many households are there in this block, and the median income of the household, and the median house value. This is something that is the most important one for us, because our model is going to predict this based on rest of the parameters. Okay, so this block, or we can call them districts, a block or a district has a population varying from 600 to 3,000 people, and Blocks are basically block groups or blocks are the smallest geographical unit for which Bureau, US Census Bureau published the sample data. All right. So our model should learn from this data and be able to predict the median housing prices in any district. So quickly, why do we generally use in most of the work wherever we are talking about the center of the data, instead of using average, we are using median? Any idea? Anybody? Why do we use median instead of average? Yes? Bintao, James, Ross, Shiva. Why do we use median instead of average mostly? Correct. Thank you, Bintao. So basically, the outlier issue, so median is the midpoint of the data. Yes, so is the average. But if any of the data points have a really unrealistic value or outlier or greatly varying data, then average could give us really bad result. Imagine that we have computed average of some numbers and we are happy with it. Suddenly one really huge number, say 10,000 comes into the whole data set, then the average would suddenly jump. But median, since what is median? Median is sorted data and we pick the middle two values. Those two values are going to remain as such because median is not going to get impacted. All right, wonderful. So great set of answers. So now, coming back to the problem. So what exactly is the next question that you must ask when you are dealing with any machine learning problem is that what business objective are we solving? How does the company expect to use it and benefit from the model that you're going to prepare? And basically, these questions should help you frame the problem, which algorithm to select, performance measure to evaluate the model, and efforts required to tweaking it. So the answer is that your model is going to sit in the pipeline of prediction of, it is going to sit in the pipeline as part of the another machine learning system. So the system will determine whether it is worth investing in a given area or not. Getting this right is critical. Okay. So basically your model is going to sit in a pipeline, in other pipeline where your model will predict prices for other users, like whether you should invest in that area, how much, as in how much loan is needed in order to take a house there, and so on. So basically, your model is going to fit in to another workflow or another pipeline. Okay, so that is the solution. The next thing that you must ask is current solution. What is the current solution? The current solution, if any, it often gives a reference performance as well as insights on how to solve the problem. So once you have the current solution, as in you know that the current solution is giving this much error, then you will be able to target that much error at least so that you have a baseline. As well as if you look at the current solution, it generally gives you more insights about solving the problem. So the answer in this case is that the current mechanism is done by experts, and their error is about 15%. The error rate of these experts is about 15%. Now, the next question you must ask is what kind of machine learning problem it is. Is it supervised, unsupervised? Is it classification or regression or something else? So is it supervised, unsupervised, or reinforcement? Anybody? Correct. It is a supervised task. Classification or regression or something else? Yes. So this is a supervised learning task, that too a regression task. Now, next question is, should we use a batch learning or online learning? In this case, since we will train it again and again on the entire data set, we are going to use the batch learning. All right. Now, before jumping ahead, so let's the one important definition that we need to know is that there are variables in a table. There are various kinds of variables. One is the numerical attributes. The others are categorical attributes. And you can say that there are third kinds called textual data. The textual data, which is part of NLP, that needs to be converted into numbers. Okay, we'll talk about that in a brief after a while. So most of the variables are either numerical or categorical. Categoricals are those which have some name instead of a number in the column. So categorical variables are further of two kinds. One is ordinal and other is regular. Ordinals are those that have order. For example, high, low, medium, or very high. So that's ordinal categorical variables because there is an order in them. Okay. While if there is no order in the values, then we call them regular categorical. Okay. So quickly, the one is what is one? Is it numerical or categorical? Two is numerical or categorical, or so feel free to also tell if it is categorical. Then does it have ordering and so on? Does it have some inherent ordering in the data? Thank you, Binta, for that answer. All right. Question is it the quickly, what kind of variables are these? 1 and 2. One is numerical, second is categorical. Perfect. Perfect. All right. Great. Now, the next is we need to further frame the problem. So there are one more definition that we need to learn. That is root mean square error. So if when we have to compare two numbers, it's really easy by just subtracting them and dividing by the actual number. It's really easy. But when we have a list of numbers and we want to compare another list of numbers and we would like to see how much are we off or how much is the percentage error, then in that case, we generally use root mean square as the way of comparison between two lists of numbers. Okay, so we want to predict, the house value based on house area in the square feet. So, and let's say we use something called univariate linear regression. What does it mean by univariate linear regression? It means that we are doing the regression or linear regression by using only one variable. Let's say we are only using one feature called housing area. Okay, so let us say we want to predict the house price based on house area. Right? So house area here would be considered as a feature. Had we been predicting on multiple values, Had we been predicting on multiple values, then we will call those multiple values as the features, right? So the input data's attributes are called features. So, right? Let us say this is the plot. This is how we generally do used to do earlier. So all we did was we let's say we only have one parameter called housing value, and that is a function of housing area, okay, or house value, which is a function of house area. So we basically plotted all the data points. So here it says that for this area, this was the value. For this area, this was the value. For this area here, this was the value. And for this area, this was the value. And for this area, this was the value. So here, since it's just a couple of data points, so it is easy to do it even manually. So how would we do the prediction here? Okay, how would we do the prediction here? So if we are using, say, linear regression is the easiest one to visualize. That's why we are using it here. Okay, and so all we do is we draw the straight lines. We draw the straight line like this one and compare how much is the difference between the actual versus the actual versus the hypothesis. Let's say we draw this line. So here, this is our hypothesis. This is the model that we will call. So this is our hypothesis or model. These dots that you see are the features, and these dots that you see are the instances, and we are using one feature called house area, and target variable is the house value. Okay, so this is our target variable. Now, there is a difference between actual and predicted. So as per our model, for this house price, this is the predicted value, and this is the actual value. Okay, then for this house, for this house area, I actually said house price. So for this house area, this is the predicted house value, and this is the actual house value. For this house area, we have this as the predicted and this as the actual. Similarly, for this house area, as per our model, this is our model or hypothesis, which is giving us this prediction, okay, and the actual was this. So this is basically, this much is the error that we are suffering. So we have 5 data points, so there are 5 errors. Now, how would we come to a single number? Is by first subtracting the actual versus predicted, the squaring it, and then summing it up and dividing by number of points, and then doing the square root. So if this number is more, that means our model is bad. Okay, so generally we put a negative sign before it, and then we minimize that error. Okay, we minimize this error. All right. So, or you can say that we basically minimize root mean square error. Okay, we don't put a negative in front of it. So this is the root mean square value. So all we are going to do is we're going to draw multiple lines on this plane, and then we are going to predict. We're going to pick the line which is best fitting into the model by computing all the root mean square error for all the data points, and then comparing that. Okay. Then comparing the root mean square error for all of these. So this is the, okay. Okay, so basically this is another definition that will keep on coming again and again. And that's it. Now, moving ahead. So the next step, we have already done this step, is to get the data. So let's move ahead. All right. So this data that we are looking at has 10 attributes. These are those 10 attributes. And one of the attributes is the median house value. This is our target variable, while these are our features of, well, except for the median house value, if we remove that column, then the data set would have only the input data, the instances of input data, and with the each column is called as feature. Okay, so let's go ahead and try all the steps. Okay, there was a question how, okay, good question, Shiva, let me answer. How did we arrive at the predicted values? How did we arrive at predicted values? I hope that is answered here. So we basically drew a line, just a random line, and then predicted value is basically for the same house area like this one. Okay, let me, okay. So, okay, let me, I wanted to draw something. Okay, so basically, if you take a look at this one, here for this house, let's say for this data point, right? This is the actual data point. So for this, this was the housing area, right? So if you draw a line like this, right? So this is the actual, and this is the predicted value. Okay, so that's how we came up with the. Okay, that's how, this is my predicted value. All right, did that make sense to you? A question from James is, it was just a linear fit, a straight line with with the least error to the obtained data. That's correct. Just to describe the meaning of root mean square error with a proper example. All right, that's why we did that. Correct. All right, so now the another important function here is housing.info. It tells you about number of records in this data set, how many values are missing. For example, there they have some missing values while rest of the data is okay. All right, so next we move then. Okay, so okay, let me just change this to cell type to markdown, cell type to markdown. Okay, so all right, so we loaded the data, then we are moving ahead and we are printing the info of the data, and then we are doing the value counts. Okay, further we are describing the data. Value count means that for each category, what is the distribution of various values. Okay, this is the categorical variable. Okay, then we are moving ahead. So here this is a very important function called housing.describe. Housing.describe has so many features, longitude, latitude, median age, total rooms, total bedrooms, population, household, and median income, median house value. Okay, so for this column, these are the many records are there, and then there is mean and there is standard deviation, and then minimum value. This row represents 25% quartile, as in, what does it mean? It means that what is that value of longitude below which 25% of the data is covered? What is that value of longitude below which 50% of the data is covered? What is that value of longitude for which 75% of the data is covered? So this actually tells you a lot about data. So generally on a data set, you should just do housing.describe or dataset.describe to get a picture of what is going on inside that. All right. Good. So now that was an overview of the data. So now next way of so we are just browsing around the data right now. So the next step is to just plot the histogram and take a look at the data. Okay, so let's take a look at the histogram. Now to plot the histogram, we are first importing the matplot inline so that we can draw inside Jupyter. And then we are saying import this particular class or package as PLT. So PLT is an object. Okay, you can say PLT as an object whereby we will be able to call a methods on it. Then we are saying housing.hist. This is giving us the histogram. And then finally we say plt.show. So this is how it is plotting the result. So here we are saying show the histogram. We're saying restrict the total number of bins to 50 unique bins, because the way it is going to compute the histogram is for each bin, it is going to count how many users are there in that bin, or how many elements are there in that bin, and then we'll do that for all. Okay, why we need matplot inline? Because in order to plot it inside Jupyter, we generally need matplot inline. Okay, instead of plotting it on the canvas. Okay, so let's just try if it works without the inline. Okay, so it does. It does work fine without the inline as well. Okay. All right, so great. But generally we need this particular statement in order to keep it in line. Okay, so percentage is generally the special commands of Jupyter. For example, let's say you want to print how much time something takes. Okay, let's say you want to find out how much time does it take. So you could use these special commands of Jupyter like percentage time or percentage matplotlib. These are the special commands of, these are not really from Python. This is especially for Jupyter. Okay. So you can always put percentage time in front of anything. So like percentage time, we have percentage matplotlib and so on. All right. Good question. So now the next part is, after we have plotted the histogram, let's talk about some observations. Okay. So what is your observation here when we take a look at, say, median population, right? So here, take a look at this one specifically, or let's take a look at this median house value. Okay. So you can see something here. While the rest of the curve looks okay, suddenly the last values have just too many numbers at that value. Say, for example, even in this one, there is an extra. The last value is really high. Why? Correct, correct. There is a stop value, or we have capped the data, right? We've capped the data. So basically, when you look at this kind of graph, that the last value is suddenly gone up. What does it mean by y-axis in here? What does it mean by y-axis in this histograms? On every histogram, or we generally call it normal curve or other kind of curve. So on any kind of histogram, on y, it's the total number of instance in that bucket, So we break down each of the data into multiple bins, and then for each bin we compute how many records are there in that bin, and then we plot it. Okay, so basically here there are too many instances on particular value because of probably we have capped the data. So this data is capped, and we should generally ask this question to the people who have provided you the data, that is it some error, or you have intentionally capped the data. Okay. Okay. So, all right. So even look at this, that the median house value, the target attribute or target variable is also capped. Okay. So in these cases, we should generally consult with the team that if it is a problem or not. If the team says that they need precise predictions, even beyond 500,000, the upper value, then we need to collect the proper data. Okay, this is not sufficient. Let's say here the median house value, this is what we are trying to predict. And in case, let's say they want the predictions beyond this value, we can't do that because we have no information about the value beyond this. Therefore, this data cannot solve the problem of predicting beyond this value. And even if it does, we will have no way to compare it. So, all right. So these are basically the modifications that could lead to the minor errors in our prediction. That's right. Good. Thank you, Vinta. Now, moving ahead. So this is now. So we basically plot the histogram, and to understand the layout of the data. The other kind of thing that you see here is there's just too big a tail. There's just too big a tail. There are one or two data points here and there. So we have the tail to be really, really sparse. Here, the tail is really sparse, so we need to tackle this problem. So these are tail-heavy histograms. So many histograms are tail-heavy. This is harder. This makes harder for machine learning algorithms to detect pattern because we have rarely few data points, that too very, very much spaced out. So we will transform these attributes to make it more look like bell-shaped distribution. Now, before we start poking around more in the data, the first thing you must do is split the data set into training and test. So we generally split the data into training and test. Basically, training is the larger size and testing is the smaller size. Here we are taking 80% of the total data for training, and remaining data we are leaving it for testing. Now we are going to train our model on the training set, and once model is trained, then we will compare our model with the testing set. So whenever we are doing predictions, even when we're building any kind of machine learning model or any kind of predictive model, we must have the testing set. Otherwise we will never know whether our model is performing great or not. Okay, so if we don't have sufficient data, we must get sufficient data so that we can split it into 80-20. So we basically randomly split we shuffle the data randomly and then split the data in two parts in 80-20. So So basically, why are we creating test set right now? To avoid the snooping bias. Snooping bias is a big issue that we end up looking at the whole data and kind of make up the patterns. So brain is an amazing pattern detection system. We look at the data and we will figure out some kind of pattern, and then we will use that information and we'll think that our model is perfect. But with real data, it may not work fine. Okay, so we are very much prone to overfitting. We'll come back to overfitting very soon. So we will. All right. So we'll basically look at the data. We'll try to fit it. We might end up going with a particular machine learning model and so on. So when we keep on looking at the data as a whole, we end up with snooping bias. Okay, it's like in the exam sheet. While preparing for exam, we just look at the answer sheets and memorized everything. Okay, so or we looked at the answer sheets and we kind of formed some kind of pattern and memorized it. Or let's say we have, so there are many snooping biases, and memorizing is one of them. So, as in memorizing is one of the effects of snooping biases, or one of the examples of snooping biases. So we are going to use a function from Scikitlearn called train test split. And let's do it right away instead of further exploring the data. So we're going to use train test and split function to create the test set. All right. So Scikitlearn provides this function called train test split. It takes from you the data set, the fraction, how much you want to choose the testing set, and then it returns you the two data set, training and testing, well shuffled. Okay, it's useful to separate data frames for labels. Okay. It is useful if we have to separate data frame for labels. Okay, so we can do that now. This is how we are going to use it. So first argument is housing the data set. Second argument is how much test size do we want. The third argument is the random state. Okay, third argument is something that I would like to discuss. Yes, Sklearn, SK without E, Sklearn is short for Scikitlearn. It's basically Scikit, SCI Kit. Okay, Scikitlearn. So Sklearn is that. All right, so yes, you are right. Next is an important concept called random seed. Okay, this takes. All right, so let me just show you the effect of random seed first. Okay. So whenever we are generating the random data, you see, every time we run it, it is giving us a different random number. Okay, it's giving us a different random number. You see that? So we definitely want random number, but not while building the model. While building the model, okay. So a question from Abintao is, do we call sklearn or scikit-learn as a library or a package? It's basically a both the words like library and package are the same thing, and we'll use them interchangeably. So it's basically a package that is nothing but a library of all the functions and various other sub packages in the machine learning world in Python. All right. So good question. So let's move ahead. So here I'm trying to show you that if we do this here, we're importing NumPy and we are giving NumPy as a name and P. If we don't do this, we will have to use the full name, right? We'll have to use the full name like this. Okay. But it's a general practice that we call NumPy as NP. So here, every time we run this cell, we get a different random number. Sometimes we don't want that. Sometimes we want to fix it because of two reasons. One, let's say we are splitting this data. Let's say we are splitting this data, and every time we are getting a random subset, right? So our algorithm as well as us, we will end up looking at the whole data because every time we are getting a different training set. Therefore, by end of few runs, say by the end of 10 runs, we will end up looking at the entire data, and that could lead to snooping biases. Okay. The other reason is that we want to fix this randomization. The other reason for fixing the randomization is that I want to kind of have a little bit more predictability so that you and we both get the same results for this discussion. That is another reason. So as long as you have the same seed, you will get the same random number. You need to call the seed before calling any random function. Okay. So this is also called seed. This is also called random state. Okay. So every time it will give the same results. If I change this to some other number, this random number is changed, but the value. So the value is still fixed, but different value. Okay, so I hope the idea of random seed is clear with everybody. So we're going to use this random seed as 40. Now, when we are splitting data, you can see first we are saying from model selection. This is one package. We are importing this function called train test split. Okay, we are importing train test split. So train test split is a function that we are importing, and to this function we need to provide the data set. Second is test size, and then random state. Why? Because this train test function gives you the two parts, training and test, the two data set it will give you, and it will shuffle before giving the result. So it will basically randomly pick the test set, 20% of the records, and mark them as test set and remaining as training. So since it is shuffling, therefore there is a random function there, and for fixing or for making that fixed, the split, specifically for learning, we are setting a random state. We are setting a random state to 42. All right. So I hope that makes sense. So here we have splitted the data set, and we can see that these are the lengths of training and tests. A question from Bintao is, what is the difference between random int, and rand with numpy? Rand with numpy is basically Okay, let me say, if you go np.random and then press tab here, it will show you so many functions. You can see so many functions. Out of these, we are using ren and random int. So let me also see what it means. So I think these two things give you the same results. Okay, this and this are, I think, the same results. Okay, so let me just fix it, this one also here. Okay, so you can see that both of these functions are same. All right, they actually even follow the same pattern. Next is the random int. You want to keep on giving it a shot. Okay, so let's see if I fix this. So this random seed stays only for one call. Okay, you have to call this random seed again. Okay. So random int basically gives you a random integer out of what we are passing a variable here. Okay. So you can see that. So essentially, this random int gives you the value between 0 to that value and randomly selected. Okay. Good question. So moving ahead. Yeah. Now. All right. So we have. Okay. So this is the data set that we have picked. So we have split the data. Now, we can also plot the histogram of the entire data set. Okay, so you can see the histograms. Now, a very important aspect of the data. We suffer always with the sampling biases. Okay, so just now what we did was we did the pure random sampling. We did the pure random sampling, and the pure random sampling works fine if the data is large. Else we have the risk of introducing significant sampling bias. Let me talk about this. Let us say in a survey, let's say in a survey, a survey company in the US decides to call 1,000 people to ask them few questions. What is the best approach to pick 1,000 people? We cannot just randomly pick 1,000 people. Okay, there are a few reasons to it. Samples must be representative of the whole population. Otherwise, you will have sampling biases. Say, for example, if you are just picking the people who are available nearby, in your company, in your school, in your neighborhood, so you just picked 1,000 people randomly from your nearby areas. That is convenience sample. Convenience sample is whosoever you got conveniently is the convenience sample. So sampling in sampling bias, convenience sampling bias is a big problem that whosoever we got, we didn't conduct the survey, or we end up just asking. Right? We end up just asking our parents or our brother or somebody who is conveniently available to get the feedback or get the inputs. Second is the voluntary response. It occurs when the samples have strong opinion on the issue. Okay. Say, for example, you want to conduct a survey that should the West intervene in Syria, right? So the people who will strongly say no, there could be people who have very strong opinion on the subject. They will come out and vote more, and hence and hence there will be always a voluntary response. There will be the other people don't think too much about an issue, but there are some people who are um, who have strong opinions. So they were the ones who will be most available for the survey or in the sample, and hence our sample may not be representative of the whole population. Then the non-response in the same line on the opposite of the voluntary response. If most of the data set or most of the people selected have non-response, then another sampling bias. All right. So to overcome various sampling biases, we have these three strategies for sampling. One is simple random sampling. Simple random sampling is the most simple one. Given a huge population, you just sample some of the data points. Second one is stratified. We basically create stratas and we pick from every strata, right? Let us say that in a class we have 1,000 students, but there are only 10 girls in this 1,000 students class. There are only 10 girls. So we will end up, let's say we take the sample and we get no girl in our sample data. Therefore, our sample is not representative of the actual data. So instead of just randomly picking, say 50 people from 1,000 students, just randomly picking 50 out of 1,000 students, we pick some percentage from all the strata, some percentage from the women, some percentage from the men. So that is stratified sampling. In a stratified sampling, we create this strata. We create this strata and we pick the random values from each strata instead of picking randomly from all. So here is an example of. So the next strategy is, the next important aspect is creating clusters, but that one is rarely used. So what we do is we create clusters just like in the second approach, and then we pick few clusters, and then we discard, we basically select few clusters as samples out of these. Okay, so that's also one strategy. That one is used in the cases where you have humongous data. Like what we did actually is the data that is given to us is actually the cluster that is given to us, right? So we are actually, when we did the sample random sampling, we are invariably just picking few of the blocks, right? So that's actually cluster sampling that's happening under the hood, because that's the kind of data that is given to us. So cluster sampling is, again, sometimes it is enforced because of the data, and sometimes we have to do it because if the data is really huge. All right. So now this is an example. These are the examples of sampling biases. Now, here is another example of sampling biases. Let's say US population is composed of 51.3% female and 48.7% male. A well-conducted survey on 1,000 people in the US should try to maintain this ratio in the sample. Okay, this is called stratified sampling. So whatever ratio we're looking for, we should get that kind of number. And in our case of in our database, we are going to do the same thing. So we divide the data into stratified sample stratas, and then we sample from each stratum. Let's say in our case of housing prices, we come to know from experts that the median income is a very important attribute to predict the median housing prices. So we will first finish this part. Yeah. Okay, good. We are on the right track. So let us say that some experts advised us that median income is an interesting aspect, interesting attribute. It is very important attribute to predict median housing prices. Then the test set should represent various categories of median income, because we come to know from the experts that yes, the median income is a very important aspect. Therefore, there could be a case that certain people in that income group, we may pick lesser number of those than the other, right? So therefore, we would create a strata based on median income, and then median income, and then we'll basically create the categories in the median based on median income, and then we pick from each categories, or we call them stratas, for our machine learning, because we don't want to ignore a particular income group. We don't want to skip or take less data from the income group. Therefore, we will create the stratas in the income group and then pick equal percentages, that 80% from each section. So it is basically an all-inclusive kind of an approach when it comes to the statistics, or when it comes to picking the data set, right? So let's take a look at the median incomes histogram. So what do you observe? What are your observations here? Anybody? Okay, there are quite a few discussions that I missed. Okay, so let me just take a look at the questions. All right. So question from Binta is that random n gives you the range 0 to 1 even distributed. Okay. I see. Okay, so all right, so random n gives you this. Okay, so we can just take a look at the help. Okay, so yeah. All right, so yeah, thank you, Binto. I think yeah, those could be the differences. We could just take a look at their manual. Probably the manuals are the best way to just look at. Let me insert one more cell and say help, and here we go. So it's a built-in function for random sample, and okay, so it's basically, yes, it's continuous uniform distribution like this one. Okay. And what was the difference here? Let's just say, okay, so it says that this is a convenience function. Okay, so actually you should just use either of them. They are actually interchangeable in my understanding. That's why they're actually giving the same answer. Okay, so they're interchangeable, both random and random. Okay. Question from Siva is, that's why our exit polls go so wrong many times. Correct. A number of times, these exit polls actually follow the stratified sampling and these mechanisms that we just discussed, but sometimes while conducting exit polls, they don't follow those statistical principles. A question from James is, not quite. NumPy.rand can return a matrix of random numbers. Okay, thank you. I think that makes sense. All right. Okay. So numpy rand can return the numbers. Okay. We'll have to take a look at more details about random functions. Okay. Good. Thank you, James. With a question from Bita is that with each stratum, the distribution is even separately correct. From each of the, we will going to pick the equal amount of numbers from each stratus. So we have okay. So sorry about that. Now, with each stratum, the distribution is evenly separated. Within each stratum, yes, that's right. Now, moving ahead, question from James is rand and rand are slightly different, and use it. Okay, okay. So let's just say, okay, so okay, so yes, rand and are slightly different. Thank you. All right, now moving ahead, good. We are doing good. So now, what are your observations with respect to this histogram of median income? Yes, it is right skewed. What else do you see here? So we have this histogram of median income. Okay. All right. Okay. So yeah. So Bintal's question is it left skewed or right skewed? So it's actually right skewed. There's too much of data this side. So whichever side is the tail, it is called that. Okay. So what else do you see here? What else is your observation? So when we plot median, the histogram of median income, you can see that in this bucket, there are these many users. In this bucket, there are these many users. In this bucket, there are these many, not users. In this bucket, as in for this median income, there are these many blocks. For this median income, there are these many blocks. For this median income, there are these many blocks. Okay. So what do you observe? What is your observation? Anybody? Feel free to unmute if you have to say something because we are just 8 people. Yes. Any observations do you have on this? Am I coming through clearly, because I don't see your feedback? Is something wrong with my network connection? When this happens, it is generally a mark of a bad network connection. Okay. All right. So you have no observation. I was seeking the observation from your side. So we have this nice histogram. What do you observe? Do you see something with this? So the y-axis, these values are total numbers of the blocks, and these are the bins. Like, these are the median income. For this median income, there are these many in the blocks where the median income is this much. There are these many users. In the block where this is the median income, there are these many households. Uh, okay, these many, what do you say, the blocks, and so on. So what do you think? What do you think about it? What is your observation? All right, no observation. Okay. So in this histogram, most of the values are clustered around $2,000 to $5,000. Okay, most of the values are around $2,000 to $5,000. You can see that, right? And so some median income go beyond 6. Some median income go beyond 6. All right. So since median income is an important attribute to predict the housing prices, it is important to have sufficient number of instances in the data set of each stratum. So we'll create the strata out of this data, and we will the random sample from each strata, just to ensure that we have the sufficient number of instances from each strata. Our predictions should be considering all stratas equally. Okay. It should not be that because one particular strata had just few elements, and when we pick the data set, that got completely ignored. Okay. So we basically, if we do that, each stratum will have to make it such that each stratum is good enough or large enough. So we're going to limit the number of categories of the median income. Okay, so let's divide the data by 1.5. When we divide something by 1.5, if it is 15, the range will become from 0 to 10. If earlier the range was from 0 to 15, if you divide by 1.5, what will happen? This range will shrink from 0 to 15 to 0 to 10. All right, that is basically divide median income by 1.5. Okay, so that we have a smaller range. So this is something that we have done here. Now, after doing this, there are some values still beyond beyond 5. Okay, so we set or cap them at 5. So you can see that after we do this, we have the values for 1, 2, 3, 4, 5, and so on. There are not too many strata and so on. Okay, let me just run the. Okay, this can be deleted. Okay. All right. Thank you, Ross and Siva. Ross's point is majority of samples on the lower end. That's yes. Okay. Majority is between 2 and 4.5. That's correct. And cut off at 1/3. All right. So cut off at 1/3. Okay. Cut off 1/3. Okay, do you mean that within 1/3 of the data, everything, most of the data is there within 1/3 of range? Is that what you mean by cutoff? Okay, good. Let's move ahead. So here, this part we have already covered. Now we are drawing the, okay. So this is our median house income histogram. Okay, now we are going to use a function called ceiling. What the ceiling does is it basically rounds the variable to the upper value. So 1.1 becomes 2, okay? 1.2 will become 2, and so on, right? And 1.6 will become 2. So every value between between 1 to 2, okay, or 1 not included, as in even if the value is slightly bigger than 1, like this, then also it becomes 2. Okay? So all values bigger than 1 will become 2, or if it is 2, then it becomes 3, and so on. That is what ceiling does. Now, we are going to divide this with 1.5. And what is this? Housing is a pandas data frame. Housing is a pandas data frame, and this is basically a series object. A column is called a series object. So we are dividing it. If you divide a series object by some number, all of the variables will be divided by that number. Okay, all of the variables. So you can see that it has divided all of these numbers by 1.5. Now let's do the same thing here. First, we divide all of these numbers by 1.5. So the whole series is divided by 1.5, and then we are saying NP ceiling. NP ceiling basically will do the magic of um, picking up the ceiling value for all of the series values. Okay, so whatever is the output of this one, all of those column values, all of those row values for that column will be converted into the ceiling. Okay, so when we say value count, now the value counts are actually low. It's only from 1 to 10. Now, it doesn't make sense to have the whole tail because there are only few values after 5. So let's cap them at 5. Okay, let's cap them at 5, and this is how you cap them. If housing, this particular value is less than 5, leave them as such. Otherwise, set that as 5. Okay, so this way we can create the categories. Okay, so you can see that we've created 5 categories: 1, 2, 3, 4, 5, and so on. Okay. Now, to pick a random sample, we could use simply the stratified shuffling split. So, okay, this is, okay, I've just put hello, just to show that this loop only runs once. Okay. So here, stratified sampling looks a little strange, that it doesn't really work exactly like the way our previous function did. Here we are passing how many splits do you want. Okay. Second, the test size. Okay, with the stratified sampling, we could create more number of splits. Then we're passing the random state. And then we're basically instantiating it this way. And then we are calling the split. And we are saying that the housing data should be stratified, should be sampled in stratified way using this particular column. There could be multiple columns as well. If, let's say, we want to split our data based on multiple columns, we want to pick the stratified sample based on a particular multiple columns. based on multiple columns, then we can specify that here. So that's the reason why it runs, it is a loop, okay? Though this loop only runs once, and so on, right? All right. Okay, so at any point of time, we can actually just take a look at the help documentation, and I would need to see number of split is, what does it mean by number of splits? Okay, number of reshuffling and splitting iterations. Okay, okay, so it can do the splitting iterations in multiple times. Okay, and so on. So that's about shuffling. Take a look at the manual. I think this should be good enough. Okay, so it can actually do the multiple iterations. So here right now we're just doing it in a one loop. Then you can do it in multiple loops. If we do number of split as 2, you can see. Okay, so it does the shuffling operation in 2 parts, but we would just only require one. Okay. All right, so you should try that out now. Okay. So this, you can see that here. Okay, so you can further take a look at the percentage numbers. So we can see that 35% are 3, 31% is 2. So we have created this strata, and we can see in each strata what percentage of the population is there. Okay, and you can see that. All right. Now here we are basically comparing with and without the stratified sampling. Okay, so here the way we are comparing is we are seeing the percentage of each category in the overall. Then we are seeing the percentage of each category in the random selected values. And then we are seeing the percentage of each category in stratified. Okay, so that's why we have this kind of a table. So it shows that the users, when in one category, they were only 3% in the overall, the actual data set. All right. And then we do the random sampling, and in the random sample, 4% of the population was in this income group. While in the stratified sampling, we get 3.9%, and the error is hardly 1%. But other places, the error is actually 5%. So you can see that the random shuffling leads to the sampling biases. Okay. A question from Mintao: what function of IO in the, so this is location, we're saying LOC. All right. This is LOC. So it basically, what it does is LOC, but it gives us the, okay, let me just show you this, and that should be clear. Let me take an example. Which one are we talking here? Okay, probably this one you're talking about, right? So if we want to pick something from something based on the indexes, we can use LOC. Okay, LOC gives you the data based on the indexes. All right. So if you want to select the rows, you use iloc or LOC. So that. If you want to just select columns, then you can provide this way. If you want to select columns, you can do this thing. Okay. If you want to select the rows based on the indexes, we can use loc. Okay. Now we can see that because of stratified sampling, there is less error as compared to the random sampling. Okay. Now after the break, we will discover and visualize the data to gain insights. and we will. Okay, so all of the columns are selected when we say lock, but for that particular row. All right, so great, great. So this is basically the steps that we are taking. These are the user steps that we take with most of the most of the machine learning projects. And we are going to skip some of the steps because those are basically optimizations and not really a common mechanism. All right. So what we understood just now that when we create stratas, we generally get better results, as in we get the better representation of population from all stratas instead of skewed data, instead of skewed stratas, as in there are no records from some strata and there are too many records from other strata. Those kind of problems are is what stratified sampling solves. Okay, so for stratified sampling to work, we must create our own column on the basis of which stratified sampling class would actually do the splitting of data. All right, so if you compare the results, this is what we were comparing the results of stratified sampling. You can see that in some of the cases, the random split were having the 5% of the error as compared to the actual. So in the case of income strata of 4, the overall was having 17.16% total population. And when we did the random sampling, 16.7% of the total of the 16.7% of the total records were in this strata, and in this stratified it was 17.6. So the error of random as compared to the overall is around 5%. So you can see that while stratified sampling has really low error, the random shuffling, the random splitting is having the random splitting or random sampling is having a huge error. Okay, so you can see clearly that this is stratified sampling error is low. That's all is okay. So now then we created the income, the split here, and so on. Have I missed any questions yet? Okay. Now, the next one is to explore data to gain insights. Okay, so let's understand the data in depth, and let's try to present and visualize the data. So if the training set is large, sample training set to make manipulation easy and fast. Since our training set is small, we can directly work on full set. Okay. All right. So if the training set is really large, we can prepare the sample. Let's say if the data is in terabytes, then since we cannot really present or visualize terabytes of data, we generally sample it for multiple reasons. One, most of the visualization tools can't handle that kind of data. Second, even if they can handle the visually terabytes of data does not make sense mostly. So we end up either sampling or any other means of converting the bigger data into small representation. So we basically generally just sample the data for presentation, okay, for visualization. Now, all right. So before we fiddle with the visualization, let's copy the training set and into something called housing, and we will basically do this part. Next is so we are going to only touch the training set. We are not going to touch the testing set. Then first of all, we are using data frame dot plot, as in the housing dot plot, and we are telling scatter plot, as in there'll be dots on xy plane. So we are saying that on x this particular column should go, on y this particular column should go. So this is how it looks like. Okay. In the meantime, is everybody executing these commands with me? So please execute that. Okay, that would keep you active and not make you feel sleepy. Okay, so here we have just created a copy and then we are plotting it. So you can see that it looks it looks okay, but it's not good enough. Why we are plotting against longitude and latitude? Because that's what a map is. Map is nothing but a plot with longitude and latitude. Okay, so here you can see that it looks okay, but we can't even make sense of it yet. So let's just put transparency. The moment we put the transparency, it starts looking a little bit more meaningful. Okay, it starts looking a little bit more meaningful. You can see that here. You can see that this is very dense, while the rest is very lighter. So now the moment we put the transparency, that magic has okay, because so it has the alpha equals zero point 0.1 has done that magic. Now in this you can clearly see that which areas are dense, which areas are dense, which ones are less dense, and which ones are sparse. Okay, so you can see that clearly based on this plot. So that's a very important okay, very important parameter here. All right, so you can see that. So these are the areas of high density. Now the next couple of more tweaks, apart from telling that this plot is of scatter type, as in we have to just put dots on the plot, and on x-axis pick the column called longitude, and on y-axis pick the column called latitude, and alpha is 0.4. We are also specifying something like this. It means the radius of each of the dot. Okay, this is S is the size of each of the dot. Okay, and we are saying that population should be considered for the size of the dot. Okay, here we're dividing the population with 100. Okay, so that it becomes a little bit more meaningful. And we put the label to this and we call that population, okay, to each dot. Then we put the color. Color of each one is basically the prices of the house. Okay, so we put two more columns. One is population and other is house value. Okay, so you can see it now. Now it is more meaningful to us. More meaningful to us. We have longitude, latitude. You see the color is actually nice. So the range of color is shown here. It is shown that the median house value is varying from hot to cold. This is basically the legend. The legend shows the meaning of each value. So here it says that red means 500,000 and blue means 0, and it starts here. So basically red represents high prices while the blue represents the low prices. Okay, so what are your observations about it? Anybody? Bintao, Siva, Josh, Ross, and Pavan, James. Siva, Pavan, James, Bintao. What are your observations on this? No observations? Okay. All right. What exactly is alpha? Alpha is transparency. Alpha means the transparent. So the magic of transparency is that if there are two parts, as in not transparent, it is translucent. Okay. Alpha basically adjusts the translucency, as in you can say one layer visible through the another, right? So alpha is that it is 0.1 means it is 10% transparent. Okay, so if you have two transparent layer and if you put one top of another, the portions which are overlapping will be darker than the non-overlapping part. Correct? It's the same phenomena here. Okay. A question is, what does it mean by get CMap? It's basically the color map. Okay. So we are saying that the color map should be of type jet. Okay. Color map should be of type jet. All right. A question, a point from Bita is that the most population is located nearby the ocean. Good. Two major centers of housing seems to be higher housing prices along with one edge of the plotted zone. Good, good, very good. All right. So yes. So basically, the first observation is that it looks like that the red ones are nearer to the sea. Okay. So first of the observation is in the high density area closer to the sea. Okay. The question is, what do you say about this? While this one is near the sea, while these parts are also near the sea, but they don't have higher values. So it's not only the proximity to the sea that matters. Okay. There are some other aspects. So all right. So it's not a simple rule. So we will have to understand the correlation with each other. And correlation essentially means that if two variables are strongly correlated, the line would look very linear. If there's a not so perfect correlation, but good enough correlation, okay, then very low correlation, right? And this one is no correlation at all. So we generally observe the correlation between independent and dependent variables, the target variables, and your input data. And there are many kind of structures possible. So in all of these shapes that you see here, the correlation is zero, as in there is no straight correlation. Here there is a strong correlation, and this one is a negative correlation. When x increases, y decreases. Okay. Now, so we can compute using CORR method, and we can take a look at the correlation of the entire data set. Okay, so let's take a look at entire data set. So you can see the correlation matrix here. See, here this is a correlation matrix. So what does correlation mean? We're comparing one versus another. There are two more points. So probably the higher density areas are already established. Okay. The question from Binta is, there are so many parameters with plot. Can you explain some important of them? Okay, actually in the plot, these 4 5 the arguments. So these are really important ones. So this one is something that you need to know. One is the kind, scatter. Okay, so take a look at, I would again say that take a look at the manual, because okay, so let's take a look at the manual. Okay, so you can see that here. So you have, when you are saying plot, we could also plot line from one place to another and so on. Okay, so actually going over the matplot will take like full lecture itself. Okay, so take a look at the manual. I think that will clear up. And there are many kind of scatter plots, so take a look at that. And then here we are specifying the one column, second column, then the size of the figure. This is the size of the figure, how big the figure size should be. Then this is the size of each data point. This is the color of each data point, C. Okay, and then we are saying color bar equals false. Okay, there is we are saying that color bar equals false. So what if we say true? Okay, so here is that color bar. Okay, which shows. Okay, so this is what it is. All right, for other colors. For other colors in between, this is what it shows the details. All right, so you can say color bar and then alpha. Alpha is for transparency, how much percentage of transparency you want, and so on. Okay, so I hope this is useful to you. Now, coming back to the correlation matrix. So correlation matrix basically compares every column with against everyone and establishes which columns are correlated. So of course, when longitude increases, the longitude also increases. Therefore, there is a strong correlation, straight line. And if latitude increases, okay. All right. So okay, so we can use the image show also to, if you have already an image, you want to show that image and render that image, you can use IMSO. Thank you, Abhinda. Okay, for the question. So this is used for showing an image at what point. Okay, so here we wanted to overlay a map, therefore we are using the IM show. Okay, good, good. So, all right, we were talking about, yeah. So IM show basically shows the California image, the one that is located at this location. And then we're putting labels, and then we're putting the prices, and that's all right. So I would say that we'll have to spend a considerable amount of time on an individual level by tweaking these graphs, and that should give you a good idea. Okay, now just give me a second. All right, so let's continue. So here again, so we are basically calculating the correlation after the graph. The next thing we did was we tried to calculate the correlation matrix. Correlation matrix basically compares one column against every other and see how are we related. So out of this, we are only looking for how are various columns related to the median house value, as in how are they correlated. Okay, so you can see in this, if I say sort ascending, so which one is most correlated out of these columns? Anybody? To median house value, what are the variables correlated? Of course, it will be correlated by itself. That's correct. Okay, so median income, yes, median income is very well correlated. Income category is same as median income, so right. So we can ignore this one. Okay, you can see already that these two are same. Okay. Okay, so yes. What else do you see? Latitude is also having a good correlation. after the total rooms, right? Even though it is negative, as in when we increase latitude, the price drop down. Okay. Next is that we can further. Okay, so let me show you. So if we have, say, 4 attributes: median house value, median income, total rooms, and housing median age, we can just plot those parts here. We can say scatter matrix. Okay, and this, let me just show you this. Okay, so yeah, now you can see that. So instead of using car, we can also use scatter matrix from pandas, and that one shows that this one is correlated really well. All right. Next is right. So here, basically, this particular attribute is very well correlated. Okay. So median income and median house value has a good correlation, and latitude has a negative correlation. Okay, so we can also look for correlation using pandas scatter matrix. So, and the scatter matrix basically look like this. Okay, every variable against every other. It tries to plot that. Looking at the data, you can quickly see that when this is increasing, this is also increasing. Okay. Okay. So now the one which is more correlated, we pick that one and we plot it. So this is how it looks like. Okay, now here there are, so this is median income versus median house value. So you can see that it is very well correlated. And there are some quirks. We will have to go over these quirks. Okay, the value is capped. Again, median house value, you can see it's capped, as well as there are these quirks which we'll have to go remove. So that's an additional optimization step. We don't need to generally do these things. Okay, these are the additional magic that we would do in order to improve the performance. Okay, next is the attribute combination. So sometimes we can add more attributes. We can add more attributes based on our past experience. But again, this is what do you say? Attribute combination is that we know something about the data from the experts that if you have this kind of combinations, it might work. So in those cases, we can use attribute combination techniques, and that should give you a better picture. Okay, so our mileage can vary from each project, but it's generally gives you good ideas. So we can add more attributes to the data. So like, for example, we can add total number of rooms or total number of rooms per household, and number of bedrooms per room, or population per household. Okay, those kind of attributes we can prepare and add to the data set. So we're creating these 3 columns: rooms per household, bedrooms per room, and population per household. This is an optional step in real project because you will never know on what basis should I create these. We generally leave this to the algorithm. It is just an extra optimization step. Okay, so you can see that after attribute combination, we have the rooms per household is actually is second highest in the all. Okay, you can see that. All right, so basically bedrooms per room is a strange one. Bedrooms per room is actually the one that is most correlated after the median income. You can see 0.25. Okay, so basically the bedrooms per room attribute is much more correlated with the median house value. Okay, let me just take a look at the chat if we have chats. All right, so let me just go over the Jupyter notebook and where are we? Yeah, here we are. Correct. So you can see that the bedroom per room is highly correlated with the income. Okay, bedroom per room is highly correlated, and this is one. So we observed the data. What we did was we did the data visualization. We understood that how to visualize roughly the data, and then we prepared the data for. We are going to prepare the data for the machine learning algorithm. So now is the time that we are going to do some important steps that are always required. We also added some 3 columns just to understand how are they related, and we saw that bedrooms per room was a strange combination that we found, which is working well. Now is a very important part. So even if you skip the visualization, you skip the attribute addition or finding a correlation, it is completely okay. So step number 3 is completely okay. We don't need to worry about that. Okay. So, but splitting the data was an important step that you will be doing that all the while. Although exploring the data is very important, but if you are not an expert at exploring, still it will be okay. Now let's go ahead with preparation of the data for machine learning algorithms. So let's prepare the data. The idea is very simple. So first is we will automate the process by doing various things like creating procedures and also creating pipelines. Okay, so we're going to revert to the clean data, whatever we had earlier. Okay, so first of all, we're going to delete this column called median house value. Why? Because this is our output or target variable. We don't want to keep it in our input data. We would keep it in another data set. So housing contains everything except the target variables, while housing label contains only the target variable. Now, data cleaning. So there are, in every data set, there are some values that are always missing. So first of all, we create functions to take care of these missing values. And like, for example, total bedrooms are lesser than other attributes. That means there are so many values missing. 207 or 207 values are missing in this. So one option is get rid of the corresponding columns, get rid of the corresponding rows, and otherwise we can fill them with some default value with 1, 2, 3, or some median or 0 or something. So those are the 3 strategies. Out of these 3, we are going to follow the third one, whereby we'll fill it with some value. These are the ideas on how to just drop a column, drop the rows, and fill the values with something. Okay, so let's experiment with these methods. So here it is trying to show you the data, and then I'll just go ahead. And here we are trying to delete the column. And here, sorry, this is where we are trying to just drop those missing values. Here we are dropping the column entirely, and here we are filling it with median. Okay, so we are filling it with median. A better technique is to use the imputer class. Imputer class basically is the one that you should be using in order to fill the missing values. Okay, the way you do is you create imputer. Strategy is median in our case, that we want to fill the missing values with median of rest of the values. That's what we are going to do. So here we are instantiating imputer. We are creating an object of imputer class, and then we are saying, then once we have created the instance of imputer class, then we can okay, so yeah, one more thing before calling the imputer, we are deleting one column from the dataset called ocean proximity. Why? Because ocean proximity is not a numerical value, and therefore computing the median of it would not make sense. So once we have removed the ocean proximity column, then we can fit. Fit means fill the values with the median. Okay, fill the values with the median. Now So after calling fit, basically it is going to, so imputer has 3 steps. Okay, let me just go back. Imputer here, using an imputer has 3 steps. One, creating an object of imputer. Second is using fit. Fit means it will compute the median of every column. And then the last one is transform. Using transform, we can transform the data set. So this will fill the data there. Okay, now let me show you this. So the imputer transform actually gives you a NumPy array that you need to convert back into pandas if you want to. Okay. So there we are. I'm just going ahead. Okay. All right. You guys should also do it parallelly. All right. So this is where we are defining an imputer class, and then all right. Is my voice clear to all? Are you able to hear me? Okay. Okay. Let me just check my audio settings. All right. I think my mic is still used. Oh, all right. Is it better now? So it was actually using my laptop's default mic instead of using the headphone. Okay, so so first of all, we are right importing from Scikitlearn pre-processing the imputer class, and then we are creating an instance of it. Okay, here, and then we are removing the ocean proximity column in from housing, and we're creating new one because this one will not really drop from housing. It will basically just return another data frame which does not have this particular column. Okay, now then we are fitting it. Fitting means computation of the statistics like median median of all the columns. And once we have fitted, then we can transform the data. I'll answer your question, Vidya, very soon. So then we can transform the data. So you can see clearly that this data set, okay, is a NumPy array. Is a NumPy array. You can always use the type method from Python to know that. So you can see that we have just transformed our data into something that doesn't have nulls. Okay, then we can create a data frame out of this by passing the number of columns, the column names, and as well as the NumPy array. Okay, because NumPy array does not have column names. All right, so you can see that. Great. A question from Binta is, how can I know which packages I do need to import, such as pre-processing from imputer? Yes, for imputer. So imputer is this imputer. This is what I'm saying. So yes, question is, how would I know which one to use? So good part is that Scikit-learn has a very well-defined packages. Okay, Scikit-learn has very well-defined packages. I should just take you through it.
Take a look at Scikit-learn. Generally, you will get a clear picture. So, okay, so here, okay. So there is a package called calibration. There is a package called cluster. There's a package called covariance. You can see that data sets, right? In the data set, you have so many data sets available. Okay, so take a look at this. I'll just give you the URL. They'll give you a very good idea about how about what are the various libraries. All right, great, great. A question from Vinta is that what is the function of any? How can I know what packages do I need? So any, I think you got it clear, right? Any is for picking any value. Yeah. Okay, if any of the value is true, then it returns. Now, moving ahead. So now, once we have created back our data frame out of this NumPy array, what we have done is we have basically counted the values again. Now this time all the columns have all the values. Okay, that means our imputer did work. Now comes the another part where we're going to convert the categorical variable, okay, categorical variable into numerical value. Okay. All right, so we did the transformation of the entire data set. So because tomorrow, whatever data set is coming to us, the other values could also have the missing values. So right now in this data set, we don't have, but in production, we might have missing values. So instead of per column filling the missing values, we are filling the entire data frame. Okay. Now, the next important part is handling text and categorical attributes. So in our dataset, there is one attribute called ocean proximity, which does not have numbers in it, but it has a string in it. We need to convert this into numbers. So let's take a look at, say, some of the values of this column. So these are the values. We can further take a look at the value counts, and we'll get an idea about each value count. Okay, so you can see that this is one value. It says less than 1 hour from ocean, inland, near ocean, and so on. Now, the right. So, okay. So now the next point is that how do I convert this into numbers? There are two strategies to convert it into numbers. One is called factorize. What factorize does is it breaks down it gives numbers to the names. Say, for example, we have type 1, type 3, type 3, type 2, type 0. So it'll start from the left, we'll give this as type 0, 1, again 1 because it's the same value as previous, and then again, then here it's 2, then here it's 3. So it starts from left, it starts giving them names, okay, giving them numbers actually. Now, so this is how it looks like after factorization. So it also provides the category orders, like you get to know that in what order we have 0 and 1s. Okay. Next is all right, so this is how it'll look like. And in the previous example, whatever we are doing, machine learning algorithm may assume that two nearby values are more similar than the two distant values. Okay, therefore, this one, because when you are converting something into numbers, what will happen is it'll think that the value it has given to the first two, like the one which has 0 and 1, they are more closer than 0 and 2. And that way, Giving the numbers this way may not solve the problem because they do not have a strict order between them. So what we do in these cases is we use something called one-hot encoding. What does one-hot encoding do is it converts it into columns. So let's say there was a column called VW, Acura, Honda, and Honda, right? Let's say this was our column. So what it'll do is it'll convert these values into the column header. It'll convert VW as a column, Acura as a column, and Honda as a column. Then it'll basically put 1 or 0 in the corresponding column. So for first one where price is 20,000, it'll put 1 in the VW because that's the value of this particular row. Then for 10,011, it is basically belonging to Acura, so it put a tick mark there. Similarly here, this one means tick mark actually. So if the price is 50,000, then the answer is Honda. And for 10,000, again the answer is Honda. So this way what it does is it converts the categorical attributes into many columns based on how many values it has, how many distinct value it has, and give them the 0 and 1 value based on if a particular record belongs to a particular category. So this is called one-hot encoder, and it's completely okay to use it often. And so okay, so Scikit-learn provides one-hot encoder to convert to convert categorical values to integer values and so on. So let's do that. So let's use one-hot encoder and then call fit transform. Whether these data cleaning steps or actual machine learning algorithms, they all have fit and transform two methods. So here that's what we have done. Okay, after doing this, the category looks like this. It has got 4 columns because there were 5 columns because there were 5 distinct values, and it has marked the corresponding column. Okay. Now, once we are done with converting the categories into numbers, we can just combine the normal numeric attributes and the categorical attributes after encoding. Okay, so we can use that. All right, so we have okay, so let's just show you. So this is what we were doing, and okay, so these are the examples here. All right, here we are trying to create our own encoder. Okay, so you can take a look at how you can create your own class which can be used. Okay, take a look at that. Okay, just too big to deal it in the class. So we have created something called category encoder. Basically, it will encode a category into something meaningful. Okay, so here we have housing underscore category, and these are the values and so on. Okay. All right, so it is done. These are the categories, corresponding one, and all right. Now, this step where we are these steps, whatever we are doing, they're going to be repeated multiple times. So it is better to create our own transformation function. So we have created here combine attribute method. What it does is it basically computes those extra attributes like rooms per household, population per household, and it basically concatenate that. Because as we told you that you should automate everything, this is one of the very common practice that if you're doing something again and again and you know that it's going to be used, it's better to keep the class ready so that you could fit it into the pipeline. Okay, so this was an example of creating your custom class, which can handle which can add more variables. Okay, so now We can write our own transformation tasks, such as because we are doing many steps, so we can actually couple them together and create our own methods, which can be called from the pipeline. So all we have to do is create a class, implement fit transform or fit underscore transform method, and so we can actually create one single function to do both the things, adding the attributes, okay, and then cleaning up the data. So we'll show you that. So we are just defining a attribute, this combine attribute adder. You can take a look at it. It is a useful thing to do, but not really must. Okay, because the automation will make your life really easy. So pay attention to creating your own custom transformers. Now, the next part is also important. So once we have filled in with the missing value, and we have converted the categories into the one hot encoder. The next step is feature scaling. Feature scaling, why? Because the data, let's say you have a housing data set, and there you have total number of rooms ranging from this 6 to 40,000, while the median income is only varying from 0 to 15. So we will have to bring all of them onto the same scale. We'll have to bring all of them into the same scale, so that the machine learning algorithm can perform really well. So we will basically normalize them or scale them. So there are two kinds of scaling. One is called min-max and other is called standardization. Min-max is the most easiest scaling one, where we basically take the data and convert it to the scale of 0 to 1. The minimum becomes 0 and the max becomes 1, and everything in between. So that is min-max scaling. This is the easiest one to do. And strictly the formula looks like this: for each value, subtract minimum from it, divided by the range. Okay, so it is pretty simple. So first of all, you take the data set, shift it to the 0, and then you right then you divide by the range. Okay, so you take the minimum to the 0, maximum to the 1, and everything in between. Okay, this is called min-max scaling, or we also call it normalizing. Okay, so in this scaling step, you have two kinds of scaling. One is min-max or normalizing, or second one is the standardization. Okay, so here are the examples of min-max. The second way of scaling is the standardization. Standardization is um, we this is a more common way of converting the grades in a school, from converting marks to into grades in school. Okay, so what we do is we basically compute that how much a value is away from the mean, and how much means how many standard deviation it is away. So first we compute the standard deviation. What is standard deviation? Standard deviation basically how much data is varying, and we subtract the mean from each of the value and divide every value with every difference with the standard deviation. Okay, so this is what it is. So we compute the mean, we compute the standard deviation, and then we subtract that. So all right, so standard scalar class, Scikit-learn provides a very nice method called standard scalar for the same thing, and we can use that. All right, so standard deviation is good for the cases where data is varying a lot, but it does not guarantee that the outcome of standard deviation, standard scalar, is going to be between 0 to 1. Unlike min-max scaling, in min-max scaling, it's guaranteed that the range will be converted into 0 to 1. Okay, so it basically, if it is a must to use, if it is must to bring the data between 0 to 1, use the min-max scaling. Otherwise, standardization is good enough solution for for uh, bringing your data between 0 to 1. All right, so now we can create something called a transformation pipeline. So transformation pipeline is basically a pipeline in which you can add all the steps. Okay, So let's build a pipeline for numerical attributes. Steps we have done so far is handle missing values, imputer class with strategy as median, custom transformation for adding attributes, and then feature scaling. So these are the three main transformations that we did. All right. So these are the three main transformations, and you can see that this is how we use the pipeline. So we create an instance of pipeline, we fit in all of them and call the fit method on the entire pipeline, and we get the results. So basically, pipeline is a good construct to use in case of any machine learning algorithm so that we don't have to call it individually. A question is, how can I know when and what kind of functions I need to define myself? Whenever there is something you are repeating again and again, let's say there are some statements we have to write again and again, and you see that this will be done on test data set as well as other data sets, then you should better make them your custom transformations. Okay, because those are going to be your part of the pipeline. Even in the production, when your algorithm need to be applied or your model need to be applied, the data need to be processed using exactly same scaling mechanism as you did during training time. So it is better to create the functions for most of it. Okay, multiple steps you combine into one. Okay, so now, coming back to the pipeline. So pipeline is again, it's a pretty simple concept. Here, it will be very, very clear. So we created a data frame selector. This is one of the transformer we created. What it does is it basically picks up only the attributes that we need. So it picked only those attributes. Now, then we defined imputer as part of pipeline. Anything which has fit and fit transform can be used here. Then we defined a class called attribute adder, because we added those three attributes. And then we called the standard scaler. Then what we did was we created a pipeline out of both. Okay. One is, sorry, we created a numerical pipeline first. So numerical pipeline where we selected the data, we replaced the missing values, then we added attributes, then we called standard scaler, and then we created a category pipeline in the similar way where we converted that into encoder. We converted them into one hot encoding. And once we done that, we once we did that, we can use these as a single pipeline. So here is the full pipeline. Okay, so pipeline can have another pipelines, and each of the pipeline does provide fit and fit transform. So here we have numerical pipeline and categorical pipeline. So this is my full pipeline. If I say full pipeline dot fit, it'll execute all of these. So it makes our life really easy. It makes our life really easy. Let me go up where we were executing. Okay. Okay. So you can see that, right? So here. So we can call the full pipeline to do the cleaning and everything in a single shot. So this full pipeline.fit transform on the housing data, it executed the entire things that we defined above. Okay, so this is what it is. And let me just show you. Now is the important part. Now is the very important part that I would like to focus more. Now is the part where we are training a model. How are we training the model? We are importing the linear regression here, and we are creating an instance of linear regression, and then we are calling fit on it. So at this point, it is doing the training. It did really quickly, it did the training, and now it has learned about our data. This is our prepared data returned by our pipeline. Our pipeline did the transformation. Our pipeline contains all the steps, and now we have created an instance of linear regression and called that using this. So fit means that we want to run training on this. Now this fit method takes two arguments. One is the label. This is the second argument is the label, and this one is the raw data. So label contains what? The house prices is the label. Okay, the one. Okay, so this is generally considered as capital X, the first this housing prepared, and this is considered as Y, small y. Now, so now we can test it out if it is working fine. So we just picked up 5 records here. We just picked up 5 records, and we picked up the labels of those 5 records. Then we transform those 5 records into some data, and then we use the linear regression dot predict to do those predictions. So you can see that it has predicted this, while the actual values were this. Actual value was 28,000, 286,000, and here it is 203,000. It is 340,000. Here is 326,000. So you can see that it has done some good job. Now we can compare the error by computing the mean error between the two, the way we defined earlier. So you can see that the root mean square error is about 68,000. All right. Now let's try another algorithm. Okay. A question is, what is iLock here? Right. We are saying, give me the records from 0 to 5. Okay. Give me the record from 0 to 5. Here we are basically passing the range of value from 0 to 1. If we want to pass the indexes, then we have to just call lock. Okay. So if I want, I'll just show you. So if I want, let's say, 0 record, 1 record, 2 record, no, okay, so then, okay, so we can see that some data, all right, so you can see, not iLock, I'll just say lock here. Okay, so, okay, so basically, let's see the difference. Generally, the iLock basically is used for if we are passing the index ranges. Okay, but iLock, and you can see there is difference. So, all right. So, yep. So this is good if we are, iLock is good when we are looking for values. Let's say 0 to, we are saying 0 to 2. Okay, or 0 to say 3. Okay, so in those cases, this is good. While this one is for, okay, so, all right. Okay, so I think we worked on this part during our NumPy discussions. Okay, so, all right, I'll just tell you the difference later. For now, the idea is that we just want to pick some record, let's say housing, give me the first 5 records. Okay, that's what we want to do. So these are the first 3 records, 39, 20. Okay, so this is the records that we are looking for. Okay, so, all right. And if I say 0, 1, 2, 3, okay, we can discuss it later. I'll just compare it and help you out. All right. Okay, so we'll discuss it probably later time. All right, so I'll just take it offline. For now, let's move on with, so yeah, a very important part coming up here. Okay, so here what we did was we did the predictions on some of the labels and compared the error. Now let's try some other algorithm. One of the algorithm that we used was linear regression. Linear regression is part of the linear model, and right now you don't need to know exactly what it is doing inside. Then we are using the next one we are using here is the decision tree. Let's take a look at decision tree, and here you can see that Here the outcome is 0. Here the outcome is 0. So you can see that there are no errors at all. Do you think our model is working perfectly? Anyone? Then how come it gave us the 0? So the predictions that it did, when we compared it with actual using root mean square error. So when we compared the predictions, these are the predictions. We are comparing predictions against housing labels here at this point by using the mean square error function. So the mean square error that came here is actually 0. Why is it so? So we trained our data with decision tree algorithm here, okay? And then we are calling we're calling it on some records. What exactly happened here? All right. So basically it has memorized the data. It has memorized the results. It has overfitted the data. Okay. So now, so there are overfitting and underfitting. These are the two problems with most of the algorithm. Let's say there are two kids. Let's to understand the difference between overfitting and underfitting. There are two kids. Both of them are learning maths. Okay. One of them had just learned, say, addition, and is saying that I'm done. I can solve any problem in the world with just additions. Okay. So he goes to the exam and he can only solve some of the problems and he fails. This is underfitting. So the first kid who says that I'll only learn addition and will solve those problems and everything is addition, that is underfitting, or we call that bias. Bias is taking a very simplistic model and trying to fit in the line in every data, trying to fit in the straight line into every data. That is called bias. And the second part is there is another kid. What he did was he memorized the entire book. He memorized the entire book of maths. All the sums he has memorized. Now, when he goes to the exam, he could only solve the problems which came exactly the way it was in the book. And therefore, he also fails. So both bias, both underfitting and overfitting. The second example was overfitting, where the kid has memorized everything. So, that is called overfitting, or we also call it variance. So there is always this trade-off between bias and variance. So in case of underfitting, if we try to improve the model, we might end up with overfitting. So we have to be very cautious. So that's what is the underfitting. So what we do in case of to overcome underfitting versus to overcome the overfitting, what we do is we use the cross validation. Okay. So we use the cross validation. Let me go back here. Where did we use the cross validation? Okay. All right. Okay. So now, so when you see this, what has happened is the algorithm has memorized everything. The decision tree algorithm memorized everything. That's why it gives 0 error. So what we do is we do the cross validation. What we do in cross validation is on the training set, it splits the data into a smaller training set and the validation set, and then runs it again and again, specifically like this. Let's say this is our training set. This one is training set, the full one. Okay, this one. When we say cross validation, what it does is it cuts it into folds. Let's say there are 10 folds, so it will cut it into 10 folds. it will use the first fold as the testing set and remaining as training set. So it'll train on this white section and then test on this. Okay, then in the second round it will pick the second last one as testing, and these remaining 9 folds it will use it for training. So it will do this. In cross validation, what we do is we run the same algorithm 10 times. 10 here is number of folds. We can change that to 20. We can change that to 5. So we will run our algorithm those many number of times in order to those many number of times, and then each time we will use the different testing set and training set out of the same data. So this is how cross validation happens. So cross validation is for the cases where we see the regularization we see the overfitting happening. When our algorithm is trying to memorize something, we need to use cross validation, because we tested the algorithm on 5 records which it has already seen. Therefore, we need to test the algorithm which it has not seen before. So we will train on this part and test on this instead of testing on one of this. Okay, so that's what we is cross validation. Now this is how we call the cross validation function. So we are saying cross validation score equals this, and we are saying the number of folds is 10. Okay, so let's do that. And here we are. So we are saying, yes, thank you, James. Yes, that was overfitting, too much training. It learned everything, memorized everything that was happening here. Okay, great. So in cross-validation score, what we do is instead of testing training data as well as instead of testing on the same data as it trained, we'll basically test it on another part and train on another part. Okay, by cutting it into folds. So here we have the decision tree one. So we are again, now here please note that, okay, okay. Now where are we? So a question from Intao is, why add minus before scores? Right, right. It's a very important point. So here we are trying to improve the scoring. That means we are trying to decrease the mean squared error, right? So that's why we are using negative of mean squared error. That will try to improve this one. So it will try to increase that one, and that's why it will return the negative of minus numbers, and then it will basically convert it into positive. Okay, that's the reason why we are doing that. So this is what is the answer. So here we are using decision tree. We are instantiating an object, calling that via cross validation, and once cross validation is done, we get the scores. We are printing the scores using this display function. So here you can see the scores. Now let's just okay, so now compute the same score for linear regression. We did the same score for linear regression, and let's compare it. Let's compare the result. So linear regression, the mean error was 69,000, while in case of decision tree regression, the error is 71,000, while the standard deviation in case of linear regression is 2,000, while standard deviation is 2,400. As in the variation is lesser in case of decision tree regression, while the accuracy in case of linear regression is better. Okay, the mean is better. Mean error mean error is lesser in case of linear regression. That means linear regression is better than decision tree with respect to predicting values, while the variation is lesser in case of decision tree. So this one has more little bit more bias but less variance, and this one has more less bias but more variance. Okay, so that's the way we generally look at. Okay, so Now let's try the third one. Though we are not able to differentiate between these two, there's not much of a difference. Let's take a look at, say, random forest. Okay, and then take a look at the results. Now this is, okay, so we did for a random forest regression, and let's take a look at it. Okay, so we get 22,001, and let's also display the scores. Okay, let's also display the scores of cross validation. So this is where we are running the cross random forest one. Okay, so all right, now here is a good one. So now here is the outcome of random forest. The for me it has come out to be 52,000 something. 52,000 something. For you, it will be it might vary slightly here or there. So you can see that clearly that random forest is the clear winner because mean error is low, as well as standard deviation, as in how much variation is there in the outcome, is also low. Therefore, random forest is the clear winner. Okay. Now, so this way we can compare many algorithms, and then the next step is to fine tune the model. Just 5 more minutes, and this is the last point. So this way, what we just did was we trained three algorithms: linear regression, second one was decision tree, third one was random forest. Okay. Now, once we have tried 5 6 algorithms, we pick the one which is doing really good, and then we start fine tuning it. Okay. Now, how to fine tune a model? First thing is understand various tuning methods specifically for that particular algorithm, and next thing is that we need to fine tune is hyperparameter. Every algorithm has those knobs, those parameters that we can pass to them. Those are called hyperparameters. Now, what we do is that for those hyperparameters, what we do is we basically make a list of the changes in each of the parameters that we would like to make, and then let either we write our for loop or our iterations that for each of these parameters, try all possible cross-folding tests. So that we can basically fine tune the model and
Hello, audio is gone.
Hey Sandeep, you're not audible.
All right, I got disconnected. Okay, I'm really sorry for this. Exactly at 10 o'clock, I got disconnected. All right, are you able to hear me clearly and see the screen clearly? Hi everyone, are you able to hear me clearly and see my screen clearly? Should
Yes, sir.
we?
Yeah.
So we are on the last step of the entire. Okay, let me also check the audio things. I hope it is okay. Yeah, it is okay now. All right, great. Let's continue with that. So we were at a very crucial step. So this is basically the last step of training. So every algorithm, whether linear regression, decision tree, random forest, and there are many such algorithms. They have their knobs, their own parameters, the the things that you can tweak them. So and in order to understand each of these parameters, well, we have two routes. One is we understand the meaning of each and every parameters, or we try the permutation of those. So trying the permutation has worked really well for lots of people. Okay, even if you look at the Kaggle rankers, like who have like top scores there at Kaggle and competing on algorithm, they themselves do not even know that how did they achieve it. Mostly it is because of trying all permutations, trying all combinations. So trying all combination is so common that there is a function for it that's called grid search. Grid search CV does both the things. What it does is it calls your algorithm on various parameters, and for each of the set of the parameters it is going to create cross validation set and is going to call that. So basically all you need to do is you need to create the list of parameters for each for the algorithm, and then run it and know the performance of each one. Okay, so that's the idea behind cross validation. So once you execute the cross validation search, it will basically come up with the best parameters, which are great. And for us, it has figured out that best parameters were max features 8 and number of estimators as 30. Okay, so that's the idea behind the grid search. Using grid search, we can do many things. The other part is randomized search. Now, what happens is if you have say 10 parameters and each of 10 parameters is taking 20 values, what happens is that we get huge number of permutations. We get 10 to the power, there are 10 parameters and each of the parameters are taking 20 values. Suddenly it becomes 20 to the power 10, those many combinations, and therefore it becomes impossible to try all possible combinations. And at that point of time, what we do is instead of trying all possible combinations, we pick say random 1,000 uh, permutations, and then once we have figured out best ones out of those random permutation, and then we basically use the grid search. So since every algorithm could have many parameters and we may not know, or nobody actually knows that which parameter might work great, so we might want to give a try. And sometimes we even don't know what is the range, whether the value of this parameter is ranging from 1 to a million or it is ranging from zero point 0.1 to zero point 0.5. So in such cases, what we do is first we do the random search, and then once we zero down upon after random search, we do the grid search. So random search followed by grid search is the general strategy in order to figure out the hyperparameters. All right, so the random search basically takes the couple of arguments. I'll just show you here. So here we are performing the grid search. The best parameters have come out to be 8 and 30. Okay, and let it run for a while. It might take some time because it has how many combinations it has. Sure, I'll explain the parameter grid. Okay, Okay, let it finish and then okay. Now, or in the meantime, I can just explain what does it mean by okay. So parameter grid has one thing like this. Okay, parameter grid is an array of objects. Okay, so what it does is it will first try all of these combinations. Once it has finished these combinations, then it will try the second set of combination. So it has multiple sets that we have defined. So first it is going to try these, then it is going to try these. Okay, how it is going to try these? It'll set n estimators value as 3 and max features value as 2, then 4, then 6, then 8. Similarly, then it will set n estimators value as 10, then max features value as 2, 4, 6, 8. So total number of permutations here are combinations are going to be 12. And total number of combinations here are going to be, for each value, say bootstrap, it's going to try 3. And then for 3, it's going to try 2, 3, 4. Then for 10, it's going to try 2, 3, 4. And therefore, there will be how many? 2 into 3 into 1, that is 6. So total number of combinations it's going to try is 18. Okay, so that's what is parameter grid. Now, this parameter grid, right? So we basically have looked at the manual and it says that it can be somewhere between 0 to 50. So we picked 3, 10, and 30. Similarly, we looked at the manual and it says that, okay, it can be somewhere between 0 to 100. So we just, for now, we have set these values. So basically, in case of parameter grid, we just, okay, we basically have put some random values and we are trying them out, okay, without, it's basically kind of a black box. All right, that's how it is. So since we may not know that, the question from Binta is how do you value these? Why not all the values from 1 to a million? That's right. A lot of times we don't know. That's why we generally go for something called uh, something called random for what do you call that, random search. Okay, random search. So in random search, the parameter grid is similar. Okay, okay. So in here, the grid is similar, and just the difference is here the values could be really high. Okay, there could be, these are 200 values, they are 80 values. Okay, so a question again is from Binta, why and how do you choose the value 3, 10, 30 to them? Actually, we don't choose. We have just put some values there just for our own sake. Okay, we could try with other things. There are many other combinations to try. So, and it is no way guaranteed that it is going to give us any result. So we can try 3, 10, 20, 30, 50, or whatever you choose. Okay. So when we have no clue on the range of the values, then we go with, say, random search. And what random search is going to give us, it is going to run for only 10 times. It is only going to pick 10 of such combinations and give us the result. And we'll pick the best model out of that. And then we will go back and try all other combinations using grid search, and we'll get the results. Okay, so even without knowing anything about the parameters or algorithm, we can use a combination of random search and grid search to reach the results. Okay, so this is the other way of as in, this is other way of this is one way of fine tuning your algorithm. Now, the other ways of fine tuning could be ensemble methods. So if you have multiple algorithms together in an ensemble, they generally give you better results as compared to the individual one. So those are called ensemble methods. So we will cover these things in details later. So a general thumb rule is that if, let's say, in my class, I don't know, say one person does not know an answer, he can ask the whole class and pick the answer which has the majority. That is another way of building high performant algorithms, by combining many algorithms together to get the results and present the solution. Say, for example, we just studied linear regression, decision tree, and random forest. Random forest internally has thousands of decision trees giving the and it is performing better than a decision tree. So when you ensemble multiple algorithms together, the output is generally better than the best of the ones that have been ensembled. Okay, so that's how it works. All right, so what we learned today was we learned to create the entire project end to end, and also we fine-tuned our algorithm. So these steps that we studied together, let me just summarize those in a diagram. Okay, and yeah, so okay, so yeah, let me just show you. Yeah, here. So this is what we did today. This is what we did today. Okay, this is what we did today. We took a data set, split it into training and test. On the training set, we basically filled the missing values, added new attributes, then we scaled it. Then on the text category data, we did a factorization, then we did the one hot encoding, and then we got the final data. And from final data here, what we did was we executed grid search and random search. Okay, so those are the general strategies of solving most of the supervised machine learning problems. All right, so we'll continue from here in the next coming class. I hope that will be useful to all of you. A question is how to plot the predicted value against actual value. You can just use the plt.plot x comma y. Okay, that should be good enough. Or you can just use the scatter plot as we shown earlier. All right. So if you have two series, you can easily plot it using PLT. Okay. All right. So yes. Mm, all right. I will respond to you over the email. I've noted down. There was one more question, Binta, in the last session. Could you just repeat? I could just reply in a couple of hours. Plot in the same graph. Okay. Right. So you can just generally add to the same plot and then use the show method to show all of them together. We have done it earlier in one of the exercises. Okay, all right, sure. I'll just show you an example over the email. All right, will that be all right? A question from Siva is, do you have some reading material on these models? Yes, you should generally take a look at the Scikit-learn. That has probably one of the best the documentation on that. Okay, so reading material. All right, let me consolidate my reading list and then I can share that with you. Okay, all right, let me just, okay, so this is something that a few more people have asked. Okay, I will definitely share with you the documentation that we follow. All right, Siva. Wonderful set of questions, and I look forward to see you next session. In next session, we will continue our discussion on TensorFlow. And is there any cheat sheets available? Okay, let me just see if we can prepare some cheat sheets. Okay. All right, good. We will do that. Thank you, Bintao. All right. Any other questions at this point? All right. So thank you, everyone. Thank you for attending the class and asking wonderful set of questions. I look forward to see you on next Saturday. Bye-bye. Have a great day. Yes, we are going to put the recordings in CloudxLab. And if you go to my courses, please look at this. This looks uh, difficult to find thing somehow. We go into my courses, okay? And then we click on start. And then under here, not here. Okay, so if you go to my courses, you click on say deep learning, and if you click on start there, you will not this one. Okay, so we'll have to take a look at. Okay, okay, so this one, yeah, we will share the recordings. Okay, we'll share the recordings. All right, great, great. Yes, we are going to put it, it is going to reflect in your courses. Like this one, we have from other course. Similarly, you'll see one more set of recordings and it'll be visible in the my courses. You'll be able to see that. All right, so thank you everyone. I look forward to see you next session, in next session. Bye-bye, have a great day.
Thanks, Sandeep. Bye-bye.
Bye. Bye Bintao, bye James, bye Shiva, have a good day.